that actually was inspired in a seminar by two of the organizers in the south of France 2 years ago. And I was supposed to give this seminar in Nice, but I couldn't attend at that time. Then this is the 2 years late seminar for Nice. Okay, then in that seminar, I remember Alan Premier showed this photograph about vortex reconnection in ordinary fluids. Is water. And this is an experiment by engineers, Nichols from Australia, and Lim, I don't remember. Well, they were in Australia at that time. And these devices here, okay, it's the middle one. These devices are vortex generator, like the one of in the book of Tate that you show, Andrew, that is, to us, and they have a diode here, a kind of colorant, and you can emit a red vortex and a blue vortex, which is very nice because it's an agreement of the notation that all body use for circulations. One is red and the other blue, and they are in opposite direction, and they collide almost, you know, as possible frontal, ahead. And these snapshots are in time. Then at the beginning, when they arrive, the vortex expands, something actually someone told yesterday. But it appears an instability here that you can see. This instability is the Crow instability. Well, it's not strictly the Crow, because Crow instability is for rectilinear vortices. And then this little instability makes some reconnection, and at the end appear a small vortex ring that are drifted perpendicularly to the initial momentum. And then they wait a minute, and they diffuse a little bit. I don't know. Yeah. Perhaps it's a kind of vortex sheet. I don't know. It's yeah. And no, it's water. Okay. Okay. It's not empty space. No, there is no membrane. Yeah, there is no glass. Okay. Yeah. And as I said, this is a complex Crow instability. This is a too much complex problem. Then I will show you this famous, I don't know if famous or not, Crow instability. Is a paper also by an engineering from Boeing, and this is the original picture. Then you have these two vortex trail behind a plane, actually a B-40 something, B-47, and then after a time you can observe that this deformation of the vortex filament merge with the other one, and then there is a reconnection, and ultimately you get a smaller vortices ring in the system. And this is a more modern Google picture in color, of course, and no more information, of course. We don't need more information. Okay, then I think Luca, I don't know if he used this photograph, this slide yesterday, but he showed something very similar. The situation in fluid dynamics is very complicated. This is a very recent paper. It's probably December last year or something like that, by Shmuel Rubinstein and all these brilliant collaborators. And in this, they show the dynamics of a vortex line. And in ordinary fluid dynamics, the dynamics of vortex line is very complex, in particular because it passed by a kind of very rich scenario, passing from a vortex filament to a vortex sheet. and then secondary vortex filament, even tertiary vortex filament, a kind of cascade of vortex filament that actually make things much more complicated. Therefore, also fluids are very popular and easy to drink. We switch to another fluid, which is not easy to drink, which is helium. Well, I will just one slide, of course. Then I think this problem in the helium community regained popularity, at least after this experiment by Belay, Srinivasan, Lathrop, etc., that was already discussed here, of tracking vortices with enormous stones of hydrogen. And well, they reported this vortex, this vortex reconnection, and as you can see here, I will not talk too much about this picture, neither about the introduction to the subject, because I think Luca, I don't know where it is, did yesterday a brilliant seminar on this exposition. Then I will focus a little bit more in my small contribution. Then these are kind of reference that I think are pertinent to the subject. Perhaps the original work of Schwartz looks to be very important. And more recently, Levin and Coupling, more recently, actually almost 30 years ago, used the nonlinear Schrödinger equation to modulate the vortex. I don't remember the word now. What is reconnection? Sorry. And then this is, I would say the frameworks at least. This is on Biot-Savart law, nonlinear Schrödinger, Berloff and Roberts. They study the Crow instability, nonlinear Schrödinger. Sergei, Nazarenko, and West also in the frame of nonlinear Schrödinger. This is experiment, real life. This is nonlinear Schrödinger. This paper is actually the same as, but Berloff and Roberts, the same. Well, not necessarily the same, but no more information. This I don't remember very well. This paper is, I don't know if this is a study of the, I think a study of this fonda comes from the group of Lathrop. Then it's, I think it's merged theory and Biot-Savart. Laurent Bouet, Prakash and collaborators is Biot-Savart also. This is Biot-Savart. I got this from yesterday. It's the first experimental observation of, I got by Luca, of vortex reconnection in superfluids, in real superfluids. Well, I mean, Bose-Einstein superfluids. This paper, it's the guest. And this is experiment, and okay, this I got also yesterday by Luca, which is nonlinear Schrödinger. Then the aim of this work is essentially the following. The aim of the work is the following. We have two vortex lines of different opposite circulation, and there is a kind of observation that essentially this distance separation scales as a constant, a number, times gamma, which is the circulation, times some TC, that TC is not really important, is minus T. Why is not important? It's like critical temperatures in phase transition. It's not really important. The important thing is that this number, this power, actually 1/2 is by dimensional analysis, as Luca also told yesterday, must be 1/2. But if you include other parameters, other lengths, other speeds, etc., of course, this could be modified, as Luca also told yesterday. Then the question about this A has been questioned, or has been investigated. There are many values that I found not very, I didn't found a lot of energy, but I found some ones. And this has a star because this is an analysis, a physical D of something like 2010. It's an analysis of the experimental data by Latrobe experiment. And all other are theoretical, and they range on different values. This was the first value, about 0.4. This actually they obtained 0.4, but actually what they obtain is a relation between A and the open angle, and they use the open angle of Vele and Arts, and actually they derive by their relation. There is no selection of A. And in this article, that probably Carlo knows better than me, they use various configuration of circular vortices with lines, and they range their value about this number. And in this paper, the motivation of this actually work. They have also many configurations that they study, linked vortices, what's it called? Perpendicular reconnections, parallel, etc., etc. And you could ask them if you want. What do you want? Coming. Yeah. Okay, then I will address the nature of this parameter. The only approach, only the merging. Okay. I will not care about the outgoing dynamics, as you say, the post-reconnection dynamics. The experiment in Paoletti. Yeah. Okay, good point. Yeah, interesting. Interesting. What is said, Giorgio, is that sorry. This number depends, of course, that here I put the right circulation. If I put 4, the circulation, then there are 4. There is a 2 here. Then I will get double the value of the value of A, the effective value of A. This is A will be larger, and this is what Giorgio has just said. Then okay. Yes. No, not well. Okay. These these are really different configuration. It's a vortex with a line, not Carlo. Carlo. Sorry. Okay. In Latrobe experiment, as I said, you have a string. Not a superstring, a string only, with a rock of the size of the planet of the little little Petit Prince. Okay, then you have a string with a rock of the size of an asteroid attached. Again, you have a string with a rock which is attached to a mountain. Okay. Then, can you distinguish if you have a rock, if you have only one string or you have 10 strings? Yeah, you answer your question yourself. Well, you don't know, okay? Okay, then as the real physics is hard, we need to do something more easier. I will address this problem as many bodies did, inspired in the nonlinear Schrödinger equation. Then I will address very fast, because I waste a lot of time, the vortex filament dynamics, which probably very well known for many of you. And then I will put my contribution. I hope that I will take. Then very fast, nonlinear Schrodinger equation, which I write here. I use this notation with a 1/2 there in order to don't have speed of sound equal to square root of 2 or things like that. And circulation here will be 1, of course. It appears to be, since the last 20 years, a very good model for Bose-Einstein condensate dynamics. I am the kind of person that I don't like traps. Okay, traps are well. Then I omit the trap, of course. And but for the last 40 years has been also a very good model for nonlinear optics. Actually, the fibers that we use for communication today are ruled by a similar equation like that, but with a sign minus here on a cavity, of course. What is interesting of this equation is that I don't know if proof in the real mathematical sense, but the solutions are very well defined for all times. If you start with a smooth initial condition, there will not be singularities that appear in this. Nothing will go to infinity. Nothing will. It is very, very well defined, and also has many conservation quantities. It's the conservation of mass, momentum, energy, which are the crucial quantities of physics. It's also Galilean invariant, which is very nice for superfluid, reversible, of course, and at the end, Hamiltonian. There's many, many interesting properties, therefore should be studied. Not? And it's much more simpler than fluid dynamics equation. One of the key points of this equation is that it presents solutions which are vortex. This is the vortex solution in 1D. I put the vortex in the origin of the frame of reference. Okay, here is the vortex, and these are the usual polar coordinates with an angle phi. And usually we only consider the plus and minus signs. When you plug that into the Schrodinger equation, you get this ordinary differential equation, and this ordinary differential equation has some boundary condition. It must be 0 at the origin here. The wave function must be 0, and it must go to 1 at infinity. Therefore, we have two boundary conditions. It's self-consistent, and this ordinary differential equation could be solved for many methods, but one of them, which is very intuitive, is the shooting method. If you start with a slope here, then if the slope is too large, actually the solution will go to infinity. If the slope is too small, it will go to 0, and you can do with Mathematica that I did. And this also, I need to say, that was solved originally by Ginzburg, Pitayevsky. I don't know if Gross present a numerical simulation of this vortex, but at least Ginzburg and Pitayevsky did in the 58. This is a snapshot of the Crow instability that Natalia studied 20 years ago about, well, 19 years ago. We have two vortices which are parallel, opposite vortices. And they move together into the blackboard. And well, you put a little perturbation, and instability develops, as you can see. And then you create, in this case, fourth vortex ring via the Crow instability. And these are 20 years later simulations that you can see, okay, to see the same. At that time, we didn't have films, I think. At the time of Natalia's seminar, actually, we have real slides, papers. And this is a zoom of the detail. And you see that the next one is assumed. Here is the instability, the moment of reconnection, post-reconnection, and then the vortices. And this is the detail of that. And well, then with some patience, you can count the number of vortices that you create as a function of, I apologize for the notation, of the inverse of the initial separation distance. You will understand the notation later, of course. And we saw that all these vortex, all this number of vortices are below this line, which is a little bit mysterious for the moment, but it will not be later. I hope it will not be later. And you can do the same for a vortex ring, the kind of Nichols experiment. Well, this is a simulation. And you see, if I will pass again, you see that actually you observe the same thing, that there is a scattering. Sorry? I know, I don't know if it's similar to rail instability. I need to think, but which is similar is to Crow stability. Your question is it possible to understand Crow instability as a similar to rail instability? And then I will answer you, I need to think. Mm-hmm. No. Okay, then perhaps not. It's not. Let me. Perhaps I will comment in a second. But perhaps we have. Let me comment in a second. Okay. Well, the same thing we can describe that the number of vortex rings that are emitted are below some line, and probably I will forget at the end, but there are also not always we emit. Here I just counted the vortex, but sometimes there are Jones-Roberts structures which are emitted, and they are not counted. If you count the Jones-Roberts, some displacement appear. Okay, then let's pass to vortex filaments. Then the idea is that if this is the, could you stop talk, Marquetian? It's annoying. You are in the first row talking. Can I do the same in your talk, maybe? Okay. Then you have this nonlinear partial differential equation, and the idea is to separate scales and assume that there is a coherence length, which are these sides here, and assume that every distance, this vortex filament and this one are very far away. And because they are very far away, the wave function is just, the modulus is 1, then it's just a phase, and when you plug that into here, essentially appears that you need to solve this Laplace equation for the phase, and to add the boundary condition, which are these vortex that yesterday someone says they are Dirac function, Dirac delta function, something which is feasible. And there are some, for the next, I will, okay, and the solution to that are the usual Biot-Savart dynamics. This is the dynamics of the filament I, with some, I put here the circulation, the real circulation. This is the self-interaction, and this is the interaction of all other filaments, but in this case, there is just one other filament. And of course, you know that, well, these are far away, one filament, the two filaments are far away, one each other, at least at some time. And then this denominator is always finite. But this one, because it's the self-interaction, it is well known since probably Kelvin, this denominator vanishes, then it needs a special treatment. And this, at least, I think it's very well done in Chart's paper, in FISREP B paper. And actually, the idea is that you approximate the integral of the filament over the filament, but two contributions. this integral is equal to the integral of the blue contribution plus an effect coming from a cutoff that we introduce with this parameter L, and this cutoff provides a contribution which is related to the curvature of the vortex line, and this is the local induction approximation, by the way. And then plugging the self interaction of a vortex, it comes from this integral that we will discard in the next transparency, plus the self-induction approximation. Okay? Then next transparency, I simplify things. The first thing I should say that this gamma here that I put is not the real circulation. In the nonlinear Schrodinger equation appears h bar over m, and actually it's not h bar over m because there is this log correction that we plug inside the parametrization. Then I am a little bit fast with this transparency to say this gamma is not the circulation, it's the circulation over 2 pi. That's the first message. The second message, that actually there is a rescaling of the parametrization because of this log contribution of Schwartz. And when this is an almost straight filament. The tangent is just the seed coordinate, which is vertical in the blackboard. And when you decompose these dynamics in the 2 coordinates, because here you have the 2 transverse coordinates, x1 and y1, actually you get this kind of system, which is very nice because if you multiply this by square root of -1, you get a simple linear Schrodinger equation for the almost straight filament. It is according to Hashimoto, is equivalent, of course. Oof. Then we need to add the contribution of the other filaments, theta 2, which I write with the same coordinates, and that summarized in this kind of dynamics. To say the motion of theta 1 is equal to the local induction approximation of theta 1 plus just the velocity induced by theta 2, which is this term. And similarly for theta 2. Yeah, this is the 1 over r. And as I said, I use this complex notation, which makes things much more easy. I am not the same. The first to use that, I think it goes back to Kelvin. But I don't know if, sorry, Helmholtz. I don't know if Helmholtz uses complex notation, but at least Kleinek Magda used it, who wrote first this equation. For the case that I am interested, I need to suppose that gamma 1 is gamma, and gamma 2 is minus gamma, and it will be useful to define the center of mass, well, coordinate and the relative coordinate, and adding and subtracting, you get these two partial differential equation for the capital C, which is the center of mass, and the relative coordinate will be important in the future. Little c, and this is the local interaction approximation, and this term is the interaction of one vortex with the other, which makes a drift of the center of mass, of course. And this factor 2 is because I didn't define the center of mass right. I should put a 1/2 here, but I don't like the 1/2. Okay, then I will focus the rest of the talk in this kind of model. Perhaps here I could comment about then this model, if you consider this situation of a straight vortex propagating with a fixed distance theta 0. It's mean the initial distance theta 0 plus a perturbation, and this is a solution. This is, well, with delta theta capital, delta theta not capital, is a exact solution, but of course the perturbations satisfy a kind of system like that. And looking for the perturbations, this is the usual instability problem. You see that the eigenvalues or frequencies in this case looks like that. The square root of omega is equal to, well, this number plus this other, and plus minus 2. There are 2 eigenvalues. One is always safe, the plus but the minus is negative for small k. Then this is plotted here. That means that this branch here is unstable, because when I take the square root of something negative, it has I something, and this means an instability. These are frequencies, the blue one is frequency, the other one is frequency. Then this instability is the one we are interested in. And I don't know if it's, you forgot your question, but I don't know if this could be mapped to the Rayleigh instability. Probably not. The instability source is these two, and the equation, but these two comes from here, I think. Then it's from the interaction, mutual interaction. Therefore, I don't know really. Okay, and looking for all the eigenvalues, all the wave numbers that are unstable, all that, then I can plot that it exists a k critical, which is given by this relation here, and written the k critical as 2 pi divided by lambda. Lambda is the wavelength. That means the number of vortices divided by the size of the domain. I can plot this line as I did. Then this line is the origin of that. Okay, then numerical simulations. Okay, I need to say also that actually this system is written in a very cryptic paper by Sakharov in '88, which is in the honor of the birthday of Lev Landau. And actually, Sakharov, inspired in a paper by Sidja and Pumir, wanted to understand the reconnection, and he derived this kind of this equation in the early '80s. And then was independently developed by Klein and Magna. Then I will not discuss about singularities in fluid because I don't have time, but singularities in fluid has been addressed for a long time, and I said in the and as already said in the '80s, Sidja and then Pumir, they tried to mimic singularities in Euler equation by studying the filament dynamics in the Biot-Savart frame, and this frame is much more simpler. It looks like nonlinear Schrodinger equation, by the way. So say you have temporal derivative dispersion, well, it's crossed dispersion. This is the nonlinearity, is in the denominator. Okay, I must accept something. And this is also a kind of dispersion. Then when, this is very easy to simulate, by the way, starting with a solution which a kind of small long wave mode, you can see this kind of behavior of the two vortex filaments, okay, and they come each other. And this is the temporal evolution for different times. Well, times are not linear spanned, they are polynomial, power kind of spanned, and you see that deformation starts to go and tends to go to 0. And the seed capital variable comes to a constant value, which is the propagation of the center of mass, which actually this value where it arrives asymptotically is not very interesting. Then the usual thing that we can do is to rescale the variables in time and in coordinates using Luca scaling. That means delta equals square root of gamma times square root of gamma t. And doing that, actually, we can, for the separation distance variable, actually it's scaled very well with this scaling. And also we, of course, I forgot to say, we scale the arc length coordinate. For the capital zeta, we need to shift a little bit with a zeta 0, which is, as I said, not very important. The scaling is less good, but because you have also a zeta 0, the things naturally are more difficult. Also, TC is something that you should guess from the numerical simulation, interpolation from the numerical simulation. Okay, then inspired on this kind of numerical behavior, the idea of these self-similar singularities studied in fluids in the 90s by Kadanov or all his kind of collaborators is to guess a solution which the right scaling. And then this is essentially the guess that we impose. Zeta is I times something, which is co-root, and the little zeta, which is the important one for our discussion, is the same behavior times two new functions that depend on the rescaled variable and a rescaled time. And this is a straightforward calculation, allows you to eliminate the time. Still, you have this tau variable, which corresponds to this log, eliminates the time, and you obtain we don't win too much, I must say, because you obtain still a partial differential equation for phi, capital phi, and the Greek zeta. And in terms of a variable omega, which is this number, okay? Usually, I do a little bit fast. The idea, usually, this is viewed as a dynamical system, and the dynamical system brings you to a fixed point. Then in the fixed point, this time and this time goes down, disappears, and at the end you get only an ordinary differential equation. And ordinary differential equations are much more easy to see, and we need to impose some boundary conditions. And the boundary condition actually can be seen by the asymptotic regime when t goes to tc, and I will not discuss too much, but I think, okay, these are the boundary conditions. I can see that the derivative here is 0, and we go straight in the far field. Therefore, this is the thing that we expect for the variable zeta, which is correspond to this one, and derivative 0 at the origin. And for the variable phi also goes as a straight line. And then I need to solve this system and with these boundary conditions. Of course, this number I don't know. This number I don't know neither. Our first attempt is to try to solve this as a series. And this, for instance, if you try for an inner behavior, all the coefficients A and B depends on A naught and B naught, which is not surprising because these are second order differential equations. Also, you can try an outer series, but this really does not help a lot. Then this is a dynamical system in 4 dimensions, and I don't know how to draw 4 dimensions. I can draw at least 3 dimensions, which is what it is drawn in this plot. And the idea is the following. I start with some A0 and some B0. And actually, if you try to solve this system, you can solve also in Mathematica, it's very easy. If you start with some A0 and some B0, which means that you start with some value of here, for instance, is 1, about 1, because the scaling is, the 0 is here. The system selects an C0 and a D0. Okay? This is a trajectory, an usual trajectory. You start from here, and the system oscillates, reaching a kind of constant value in infinity. And constant value of the derivative, of course. Well, because this is complex, I will show you better this first portrait. And in this first portrait, I start with 0 derivative here, with a value of A0 and B0, which are the values of zeta and phi at the origin. and then I move, oscillating, of course, till a kind of fixed point there about 1.3 and 0.7. And this can be done for all A0, as you say, all initial condition admits a solution that has the right behavior in infinity. Then, but there is a selection mechanism which is important to consider in all this kind of problem, the pinch-off of a droplet, etc. And the condition is the following. What you need to impose is that the far field do not oscillate. This oscillation, I need to eliminate this oscillation. What you see, that you see here. You see here. And there is only one set of A0 and B0 that arrives to the fixed point there without any oscillation. That's the main message. This is the usual selection mechanism in this kind of problem. And I will not, the philosophy is in the far field. You see that the far field has a solution which do not oscillate, and a second is it's a second order differential equation for the far field, which is an error-meet equation. And it has another solution that oscillates in the variable. And the thing, the selection mechanism imposed that A1, I think, A1 alpha must be 0. And that gives the value of A0, B0. And with A0, B0, the integration provides you the C0, D0. This is the idea that is expressed in this transparency. You don't need to read. Now I told you the same idea in a more graphical way. It's a kind of tuning method, but the problem is that the tuning method in 2 dimensions. Then I start with some A0 and some B0 and arrive to a fixed point. Well, he didn't arrive to a fixed point, oscillating in all cases. But you map some values from A0 and B0 here. Here we are changing B0, and here we are changing A0. Then in these 16 values, we see which is the best of all. And the best of all is around here. And then I zoom the parameters there, and subsequently you can fit very well that this is the best that I can get. Is this black curve here, is the only one that do not oscillate. And it gives an A0 1.075 and a B0 2.15. Okay. Oof. I give you the discussion. Perhaps I will give you this discussion later. Then the main message is that there is an evidence of a cell-similar vortex reconnection. The solution of this system plus boundary condition gives A0 this value and B0 this other one. That gives, after integration, C0 equal that number and D0 equal that number. And going back to the Luca seminar, zeta, which is the separation distance, is square root of gamma times Tc minus T, times the value of zeta in 0. And this is just A0, this number, divided by square root of P, because I make the warning that gamma must not be gamma really, must be gamma divided by 2 pi, because it's like that. And that gives you the value 0.427, which is comparable to, this is in this simulation, and this one. As I already said, that this kind of simulation are in a completely different situation, and there are some ideas why it doesn't work. I believe that also the log factor plays a role, and as I said, this paper actually, they don't compute the value, they use the angles to relate to the value. They use the angles by Vele and Arts. In next transparency, I compute the angles. This is actually, after some work, you can see that the angles are related to these parameters, the asymptotic parameters. And in this case, theta 1 is about 105 degrees, which is close also to Welian arcs and also close to Carlo value. Of course, Boue use, as I already said, the same thing. And for phi is about 50, which is different to Welian arcs, but is close to Carlo, which is surprising maybe. And okay, I will not talk about Jones-Roberts. Then the main message is, well, first, the nonlinear. This problem for vortex in nonlinear Schrodinger is much more simpler because the core structure is very well defined, and in fluid dynamics it's not defined. In fluid dynamics, the core stretches, and the dynamics is quite rich. Well, there is an assumption that I did, which could be discussed, that all what I did neglects the non-local interaction, the integral, the remainder integral in the Biot-Savart. It appears that the scaling makes it subdominant. And well, that's